Not clear to anyone? Does anything need a refresh?
So yesterday you told that we'll be discussing one question today.
Yeah, that we will take up. That was probably X mod X, was it? That was one of them. Then there was this X sign 1 by X. But from the
Yeah,
theory part,
that's right.
is there is there any doubt?
We're actually evaluating RHL and LHL is the concept we which want to know.
Okay, so can we do it through the problems? Is that fine?
Yeah, yeah, that's good enough.
Yeah. Okay, then in that case, let's get started. So I'll give you a couple of minutes, say until 8:17. Read the question and try to solve it by yourself and discuss the continuity means find the points at which it is continuous and the points at which it is not. So take a good look at the question. Okay, maybe 8:20 since there are like it's a four-part function. In that there will be certain points where obviously continuity will have to be checked, and there you'll have to do evaluating LHL and RHL. So this is a good place to start. So let's resume at 8:20. As in, you guys work through the problem, and then we'll start the discussion of the problem at the solution of the problem at 8:20. So any answers? At what points is this function discontinuous?
Sir, -2.
-2.
And the rest?
3 also.
Yes, sir, 3 also.
Let's check that. Does anyone have any other answer? All right, let's see. So other than the points -2, 0, and 3, so let me make the statement. Is this statement okay? Other than -2, 0, 3, function f is continuous at every point. I'm not saying that it is discontinuous at these 3 points. I'm saying that other than these 3 points, the function is definitely continuous at all other points. Is that okay?
Yes, sir.
Because everywhere else, it is addition. I mean, it's a polynomial or a composition of a polynomial with a modulus function, which is also known to be continuous. Everywhere else, it is fine. But at points where the behavior changes is where we need to pay. So -2, 0, and 3. Let's take each of them and try to solve it one by one. This is x is equal to -2 first. So whether or not f is continuous at -2, what do we need to check? We have to check whether the left-hand limit is the same as the right-hand limit. First of all, we have to check whether the left-hand limit and right-hand limit exist, and if they do, are they equal? So behavior of f to the left of -2. So how is it defined to the left of -2?
Mod x plus 1, the first one. X less than.
It is mod x plus 1, right? So if I want to check the left-hand limit, what I need to do is limit as x goes to -2 from the left, which I'll write it as -2 minus f of x, which is limit as x goes to -2 minus modulus of x plus 1. And what would this be? How would I evaluate this?
Just substituting -2 in x.
It's -2.
Just if I substitute -2 itself, I'll get this as 1. Now, behavior of f to the right of -2. In order to evaluate the right-hand limit, I need to look at the behavior to the right of -2 also. So how is it defined to the right of -2?
2x plus 3.
It is defined as 2x plus 3, right? So if I want to calculate the right-hand limit, what I need to do is limit as x goes to -2 from the positive side, f of x. And in the positive side, the definition of the function is given by 2x plus 3. Once again, a simple limit that can be evaluated just by substituting. And what I will get is -1, is it? Right. So does LHL and RHL exist? Do they both exist?
Yes.
Yes, but are they equal?
No.
No. So LHL is not equal to RHL. Therefore, f is discontinuous. at x equal to -2. This was one of the 3 points of interest. For the other two, I'll take it slightly faster because the evaluation of the limits themselves is not that hard. These are just polynomial functions, so evaluating the limit will be done just by substituting. There's no fractions or anything of that sort. So the next thing is x is equal to 0. So in this case, LHL is limit
2x plus
as
3.
x goes to 0 minus of 2x plus 3, which is 3. And RHL would be limit as x approaches 0 from the positive side. And from the positive side, this definition will be valid. So x squared plus 3. Once again, substitute and get the answer as 3. LHL and RHL both exist and they are equal. So F is continuous at x is equal to 0. So what about the other remaining point? X is equal to 3. The left-hand limit is x. As I approach 3 from the negative side,
X
3
cube
from the
plus
negative
3.
side means it would be x cubed plus, x squared plus
X
3, right? Yeah,
square
that's
plus
x squared plus, yeah, x squared plus 3, which when I substitute, I'll just get 12. And right-hand limit is limit as x goes to 3 plus of greater than 3. The definition is x cubed minus 15. So 27 minus 15 is 12.
Well,
So LHL exists, RHL exists, both are equal. So this is continuous at x is equal to 3. So the only point of discontinuity is actually -2. So to the person who said that 3 is also a point of discontinuity, did you see where you made any, maybe perhaps a calculation mistake?
Yes, sir.
Yeah. So the only point of discontinuity is -2. Maybe if we have time later, we'll discuss the differentiability of this as well. Once again, differentiability at certain points, we'll have to check for a small finite set. What finite set is that? We'll take up at the end. All right. So the next question is also a question about continuity. It's also once again finding the limit of a piecewise function, a function that is defined differently in different parts. So why don't you guys try it? But in this case, the function itself is not given, and it's not asked what are the points of discontinuity. Instead, it is said that this function is expected to be continuous, and there are certain values in which are not given outright, which you have to find. So the concept is similar, but it's a little bit the given data is slightly different. So let's resume at 8:33. 4 minutes should be more than sufficient to solve this. Oh, yeah. Answers?
A
A is
equals to
equals
minus
to
1,
minus 1
B equals to
and
1.
Once again, this is straightforward, right? Is there anyone who hasn't got this answer or is not sure on how to proceed?
Sir, I don't know, sir.
Okay. Let's go through the solution. The strategy is the same as the previous problem. This function is defined on all non-negative real numbers, right? In between 0 and 1, it is defined by x squared by a, and a, whatever that constant a is, the function is continuous between 0 and 1, strictly less than 1, because it is just a quadratic function. Similarly, it's a constant function between 1 and square root of 2. Even there, it's a continuous function. Beyond square root of 2, it is given by some constant divided by x square. Usually, when you have something like this in the denominator, you have to take care that this function is actually properly well defined. In this case, the denominator will not vanish because the denominator would vanish only if x is equal to 0. So that's not a problem. As long as that thing is taken care of, that the denominator does not vanish, you will have that ratios of polynomials are also continuous functions. So in these intervals, 0 to 1, 1 to square root of 2, and square root of 2 to infinity, it is continuous. This follows just from almost by definition. And what about the 2 points that we have not checked at? So the points of interest are x in 1 and square root of 2. At 1 and square root of 2, the nature of the function changes. So what happens at x equal to 1? Let's take a look at that, right? It's something like a quadratic equation. It might be this way or this way, depending on what my constant a would be, but then it becomes a constant. So it has certain behavior before and certain behavior after. Now, what we have to check is whether the limit of the quadratic function is equal to the limit of that constant function. Only then would I be guaranteed continuity. So what does the question ask? The question asks for values of a and b such that f is continuous on the whole domain. In particular, I want continuity at x equal to 1. So want continuity at x equal to 1. So when I say I want continuity, what does it mean? LHL is equal to RHL. Both of them should exist and they have to be equal at x equal to 1. I'm just skipping that part. Now, what is the LHL at x equal to 1? This is an equation that I need the function to satisfy.
Also,
Right?
I believe that f1 also should be equal.
Right, of course. Sorry. Yeah. We need continuity, not just the existence of limit. Have I made the same thing over here also? Right. So even over here, this can be concluded just by this not being equal. Here you also have to say f of 0 is equal to. In this case, it's not that much of a problem because it's not separately defined everywhere. So let's make this thing complete. This is also equal to 12. So all three needs to be. Yeah, thanks for pointing that out. So we need this to be satisfied. LHL should exist, RHL should exist. Both of them should be equal, and they have to be equal to the function value. And the function value I know to be, so x is equal to 1 is included in this definition, this part of the definition. So that's -1. So I'll just write this as -1. I need both, or maybe I'll write it in the next step itself. I need both left-hand limit and right-hand limit to exist and to be equal to -1. If I have this, then I am guaranteed continuity at x equal to 1. So let's see what the nature of the function is to the left of 1. What do I mean by left of 1? On the number line, if you see, this is less than 1. So at that part of the
X should be less than 1.
domain, at that part of the domain, x squared by a is the definition of the function that is applicable, right? So let's rewrite this as limit as x approaches 1 from the left of x squared by a. We don't know what this a is. We want to determine its value such that this equation is satisfied. Similarly, as x approaches 1 from the positive side, now when I'm in the part of the domain which is greater than 1, the nature of the function, the formula for the function is given by constant -1.
-1. Yeah.
Right? And both of these limits should be equal to -1. So now one part is now obvious. Limit of a constant function is just that constant itself. So this part is okay. Right? So I'll skip one of them. So this limit is equal to -1. So that is equal to what we want. So that's fine. Now, what about the other thing? The other thing, that is the left-hand limit part, that's a quadratic function. It's a polynomial function. The limit of this can be obtained simply by substituting x is equal to 1. And what would I get in this expression if I substitute x is equal to 1? I would get 1 by a is equal to -1. Now this would imply that a is equal to -1.
-1.
Is this fine?
Yeah. Good.
Yes, sir.
Right, now let's look at the other thing. The only other point where continuity could be a problem is square root of 2. The same sort of, once again, I want continuity at x is equal to square root of 2. And instead of writing everything else, I'll just write the essential steps. Evaluating the limits itself is not that hard. F of square root of 2, square root of 2 belongs to this part of the domain. So it becomes 2b square minus 4b divided by 2.
Square.
Right. So to the left, first let's see the left. That is just -1, right? I can just write this as square root of 2 minus -1. Over here, it is as we approach square root of 2 from the positive side, meaning the part of the domain which is greater than square root of 2, where the applicable formula for the function is this. And f of square root of 2 is just 2b square minus 4b divided by 2, which would be b square minus 2b. But we'll simplify it later. The first part is an easy limit. It's just a constant function, so I just write it as -1. The second part, I know that the denominator vanishing is not a problem in this part of the domain. So we'll have that identical to the last expression, which is 2b square minus 4b divided by 2, which I'll just write as b square minus 2b. Simplifying this using all the things you know about quadratic equations, or if you just observe that b square minus 2b plus 1 is b minus 1 the whole square, you'll see that b is forced to be 1. And yeah, that is the end of the problem. Now, in this case, b was forced to be exactly one number, right? A is equal to -1, B is equal to 1. But I hope you can also see cases where there could be multiple possible values for B. So in this case, we got a quadratic equation for which there was only one solution. There might be a quadratic equation for which there are two solutions, and the question may be of the form, how many values of B are there such that F is continuous? And that would be something like a numerical answer type question for which the answer is 2. Or it might be something like a quadratic, this quadratic equation that you get at the end might have discriminant negative. In that case, there is no value of B for which this function can be a continuous function. So these are all small variations of problems which conceptually have the same starting point, wherein you have to just make sure that the left hand limit and the right hand limit, they have to agree and they have to be equal to the function value. All right.
Thank
So
you,
the
sir.
next question, yeah, is this clear? We can move on to the next
Sir.
question, right?
Yes.
This is very similar. This question 3, and yeah, I've given it very less space as well. Yeah, why not just do one more of these things? I'll just give you a couple of minutes and I'll give you the answer in some time. Just take a couple of minutes. And if someone gets the answer, please let me know.
A is 1 here. Is that AX plus 2?
Where it's 1, sorry. Yeah, okay.
A would be 2 then.
And that is b x square plus 1?
Yes, bx square plus 1, yes.
Bx.
So the answer is 0.
Yeah, I'll let you guys solve it. A is equal to 2, which is also equal to B, if I remember correctly. Yeah, so A minus B is equal to 0.
So here a is equal to b because a plus 1 is equal to b plus 1.
Yeah, you could do that also, yeah.
A minus b is equal to 0.
Yeah, so without even going, so that's one nice point to observe, that instead of saying RHL is equal to f of 3, sorry, f of 1, which is 3. So this is what one would do, right? So if I substitute 1 over here, I'll get b plus 1 is equal to 3, and then b is equal to 2. Similarly, I do a is equal to 2. This is one way to do it. What you could also do is just do RHL is equal to LHL. Then you will have a plus 1 is equal to b plus 1. So you'll get the equation a minus b is equal to 0 without actually explicitly finding the values of a and b.
A and b, correct.
Yeah. One more continuity question in which you have to do a little bit more thinking, maybe. Instead of this, let me do this. I want floor here, mod here, maybe. Let's resume the discussion at 8:53.
It's not continuous at 2, sir. Is that a greatest integer function?
Yeah, the floor function, the greatest integer, no, the greatest integer less than or equal to the given number.
Is the LHL 1 and function value at is 1 and RHL is 2? Hello.
If you have got the answer, we'll discuss it in a bit. Let others also get time to do it. Right? In a couple of minutes, I'll start discussing the solution.
Here one thing, sir, mod x. Here it is given that x greater than 2.
Yes.
So when we define this function without this mod, it means that the value would be x when x is greater than 2, and value would be minus x when x less than 2.
No, modulus of x means the same, the usual, whatever modulus of x means. That is, it's plus x if x is greater than 0, if it's minus x if x is less than 0.
Less than 0. Okay.
Yeah, in fact, here having the mod there makes sense if that is what you have observed. Well, there was a reason why it was actually originally reversed. It was modulus of x less than 2. But anyway, let's discuss this. So what are the points at which the function is not continuous?
At 2.
At 2, function is not continuous. In the LHL, we get
And
value of 1. In the RHL, we get the value of 2. So 1 equals
yeah,
1.
is it continuous everywhere else?
It is also discontinuous at all the integer points which are less than 2.
Yes. Let's say minus 1, 0, 1, 2. Would this be fine? Every integer less than 2, undoubtedly, this is discontinuous. Why? Because there the behavior of the function is that of the floor function. And you know that the graph of the floor function looks like this. So there are jumps at every point, at every integer point. So the left-hand limit would tend to this value, but the function value would actually be this, which will also be the right-hand limit. So everything up until this point just follows from the fact that this function by itself is discontinuous at integer points. But of course, for 2, we need to verify it separately. But in this case, it's a direct verification. LHL at x is equal to 2. So I need to do something like limit as x approaches 2 from the negative side of f of x, right? What is the nature of the function? It is
Float of
floor
2.
of x,
Load of x.
LHL, right? So I want the greatest integer function, and for values of x less than 2, what is the less than 2 and close to 2? So what is the value of the greatest integer function?
1.
It's 1.
It's 1. So I'll just write this as 1. Now this is a constant the constant function, so the limit is just the constant itself. But then when you look at f of, is this what, f or g? G everywhere, g. What is g of 2? G of 2, the applicable formula for the function is given by this condition, in which it is the greatest integer function. But once again, you'll see that this is actually equal to 2. So LHL is not equal to the function value. So you don't even need to go to the RHL. But if you just want to do that for practice on calculating RHL, you could do that as well. 2 plus of g of x is mod 2 or mod x actually. I can just substitute because mod x is a continuous function. So this would still just be 2. So RHL and the function value are the same, but the LHL is different. Is that fine? So this is discontinuous at all of these points. So what about integers greater than 2? In the part of the domain beyond 2, this function is simply x. It's not even mod x. And that you know to be a polynomial function, a straight line. The graph is a straight line, and hence it's a continuous function.
Sir, this part, this limit x tends to 2 plus, and this mod x, though this means what is the factor? Because the mod x is always continuous, so you put the value 2.
Yes, that you can do, because since you know that mod x is a continuous function, for every point, for every real number, the left-hand limit will be equal to just the value of the function. Since mod is a continuous function, or you could also do it as when I'm in the part of the domain which is greater than 2, mod x is simply x, right?
Correct.
It's positive. It is greater than 2. So in particular, it is greater than 0. So I could remove the mod just because I'm analyzing the behavior near a certain, with a certain constraint. It's not like I have to look at it even negative side. I'm strictly above 2. So I may as well remove the mod. Now I can substitute. That is also one way of looking at it.
Yeah.
All right. So everywhere else it is continuous. So whenever you're asked what are the points of discontinuity, you have to give the full list. Just because it is defined separately, this is not the only point where things can go wrong. If the functions which are defined over here itself are discontinuous functions, you'll have to separately take care of those parts as well. All right. So next we'll go to differentiability. And well, this is a very simple thing. So I'll maybe give you just a couple of minutes. This is just to say that the product rule is not just for 2 terms. You can extend it neatly for finitely many product terms. So in a couple of minutes, I'll just give you the answer and give a general formula. for the derivative of a product of n functions. Yeah, so what's the answer?
Here we make the derivative of it, no? The x plus 2 into x plus 3, then plus 2, x plus 1, x plus 3, this kind of thing comes in.
So
You can
3x
simplify
square
this.
plus 12x plus 7.
Yeah, it's you'll get a 3x square, yes, and then you'll get a 5x, 2x, no, 5x, 3x. You just give me the answer.
5x plus 5x.
I'll believe
12x
you.
plus 7.
12x plus 11, is it?
12x plus 7.
7.
Yes.
Will it not be 6 plus 2 plus 3?
Sir, I think the answer is 3x square plus 12x plus 11, not
Yeah,
7.
it's 11 because you will get a 6 over here, you'll get a 2 over here, you'll get a 3 over here as a constant term. So anyway, the point is that here, how did you get this? One, look at the product formula is if f is equal to f1, f2, then f prime is f1 prime, f2 plus f1, f2 prime. This we know. This is the product rule. I've let go of the of x. Everywhere there is an of x, but I've just let it go. But what if there are 3 terms? So just as we do over here, we differentiate one term and leave the other. We will do differentiate one term, leave everything else the same, and we'll cycle through all the terms in the product. And if you want a quick proof of why this is how it works, you can start with this and apply the product rule
1 minute.
for
Okay. Plus f1 only f2 differentiation.
that's this, no? So you'll differentiate only f1 first, then only f2, then only f3.
Okay, thank you.
Yeah, yeah.
Right, so for the proof, you just club f1 and f2 and call it one function and use the product rule for 2 functions, considering f1, f2 as one function and f3 as another function. And to simplify this, you further use the product rule. This falls into a class of proofs which can be done by something called mathematical induction. That's not part of the syllabus, but it's something that you can lookup if you're interested, wherein you start out with the case of n equal to 1, and then you figure out how to go from n to n plus 1 and then generalize the result. In general, if I have f to be f1 to fn, product of n functions, then what is its derivative going to look like?
It is f1 prime, then the rest, then the f2 prime, then rest. This.
Yeah, so I will write it this way. Let me know if this is okay. 1 to n, where I have f1. So when we usually write this, and the edge cases where n I is equal to 1, you'll not have this part of the summation. It's a sum of n terms, and in each term, you are differentiating one thing and leaving the rest as it is. So this is just a compact way of writing this. And this was a fairly simple example of that. All right.
Sir, can we also do the product of the first two terms and then multiply, I mean, take the derivative of both the two terms like that?
Whatever
also
you
we
do,
can
you will get the same answer. So are you saying that you will just do x square plus 3x plus 2 times x plus x
yes,
plus
sir,
3?
yes. Yes, sir.
Yeah, even if you do this and solve the problem as just the product of two functions, you will get the same answer.
Okay, sir. Thank you.
You will get x square plus 3x plus 2 times the derivative of this, which is 1, plus x plus 3 times 2x plus 3, which is the derivative of this term. And if you simplify, you'll see that you'll get the same thing.
Yes, sir. Thank you, sir.
Whichever is convenient, you can use. Both are correct. If you're logically going from one step to the next, there's no way you'll make a mistake. So, right, question 6, and try to find the derivative of x to the x. So there is a standard f1 of x is a to the x, then f1 prime x. Does anyone know what the standard formula is?
X into x to the power x minus 1.
No, a is a constant over here. It is a to the x. So what you're talking about is x to the a kind of a thing, wherein you will have the derivative to be a into x to the power a minus 1. So these two are not applicable because here both the base as well as the exponent are equal to x. So how would you go about doing this? Think for a couple of minutes.
So can we take log into this?
You can. You do that and get the answer. I'll tell you, there is a very subtle point which you need to be careful about.
Okay, so I'll just do it. Sir, I got the answer for that.
What is the answer?
So the answer is x to the power x, and in brackets it's 1 plus log x.
Just one moment.
Mhm.
You're saying f prime x is
1 plus log x. Yeah, that's it. So, sir, is the method correct or there is some discrepancy?
there is a small point that which I'll point out. Yeah.
Taking log
Did
on-
anyone else? Yeah, taking the log on both sides.
Yeah, I just did.
Um, right. Okay. Let me give the solution and then we'll discuss that point.
Yeah, sure.
So f of x is equal to x to the x. One way to do it is take log of f of x. Can you take log? You can take log when you're sure that the thing you're taking the log of is a positive number. Look at domain, you have a positive number raised to a positive power, which always is a real number, and it's a positive real number, right?
Yes.
So this would be log of x to the x. And by the law of exponents,
Log x.
which you know for this is this. And now I can differentiate on both sides, right? I will do the differentiation of the left side first. It's a
F-
composition of two
F one,
functions, right?
f of x.
So you will have 1 by f of x,
1 by f
which
of
is times f prime of x. So this is an application of the chain rule. So you have a composition of log of f. So it's like log of f of x. So you'll do log prime of f of x times f prime of x. This is the chain rule. And log prime is 1 by f, 1 by x. So you will get this. And on the other hand, you will have x times 1 by x plus, yeah, the product rule
1
times log x.
1 into log x, ln x.
Yeah. So I'll take the thing to the other side, and what we get is f of x. I'll just f of x with x to the x times 1 plus log x. So this answer that is given is correct. But the catch is that we are doing this assuming that this function is differentiable, right? What is the guarantee that it is? So this is a theoretical thing. So here you're taking the log of it and then you're differentiating on both sides and you're applying the chain rule to get this equation. So somewhere you're assuming that, so what does the chain rule say? If f and g are differentiable, then f of g prime of x is f prime g of x times g prime of x. There is an assumption already that f and g are differentiable. So this is log of f of x. You know log is differentiable, that is fine. But do you know that f is differentiable? Not really. So even though it looks like a nice function, it's just exponentiation. We have not established that this is a differentiable function, right? So that is the point. This is where this is actually logically incorrect unless you already know that f of x is differentiable.
If you can
Right.
explain.
So do I need to explain this again? Is that what you're asking? Okay.
Yes.
So here, whatever the function is, taking the log on both sides is fine, as long as the arguments are positive.
I didn't get it, like f dash x is already given x to the power x and then 1 plus ln x. And the whole
No. This
entire
was the
problem.
solution that was suggested. This is the question part. This is the solution. This is
Sir?
the answer, and this is the solution, right?
Okay, if
What
x
is your
given,
doubt?
x to the power x.
Yes, that's all that is given. When it is asked to find f prime of x, what is implicit is that this is actually, very strictly mathematically speaking, prove that f is differentiable and find f prime x. So when it says find f prime x, first you have to show that it is differentiable. So when is a function said to be differentiable? When f of x plus h minus f of x divided by h, that expression has a limit. So we have not verified that. But then we
can we
applied
do
log
one
on both
thing?
sides. Yeah.
Suppose I define f of x, which is differentiable, and I also define a g of x, which I don't know is differentiable or not. Now I
Yes.
establish a function h of x, which consists of f of gx. I composite g of x in f. Then I
Okay.
prove that if the function is in a function, composite function which is differentiable, then that function has to be differentiable. Then I can do this.
If you can prove that result, then you can do this. So you're saying that let f, g be functions such that they can be composed with each other. That I'll skip. So this is not part of the solution. But if f of g is differentiable, let me give you this, and f is differentiable,
Yes.
then g is differentiable.
G is differentiable. Yes. This only.
So you're claiming that this is true, and if this is
Yes.
true, then I can go. This argument is
Yes,
complete.
I can go logically according to this argument. If I
Yes,
prove,
but is this statement true?
I should check with an example.
Well, you should, if you want to prove it, you have to give a mathematical proof using first principles. But whenever you have such things, the first kind
I'm
of
not
check
getting-
that you have.
I'm not getting the contradiction because the math proof starts with the contradiction only. That let us assume G is not differentiable. Then I prove it wrong. So I'm not getting a function which can disprove this.
Okay, consider the following. Okay, so I'll tell you that this statement is false. Okay, f is f of x. These are all real valued functions, r to r. F of x is just 1. It's a constant function 1. Okay, and g of x is whatever non-differentiable function that you want. You start out with these two things. What is f of g of x?
It is, if it is a constant function, it is 1 only.
Right?
Yes.
So this is differentiable. This is differentiable. But this is not. So this is, for a very trivial reason, this statement is false. Do you see this? Did you understand what's happening? So the non-differentiability part of G can be killed by F. That's a very vague statement, but that sort of behavior can happen. In this case, I'm using a nuclear bomb that I'm just putting it as a constant function. So of course it's going to kill anything and make everything constant.
What if
But even
we
otherwise,
use G of F?
Yeah, go ahead.
What if we use G of F?
even then, I don't think you're saying g of f is differentiable and f is differentiable, then g has to be differentiable.
Yes.
That also, I think it is not correct, but I'll have to think a little bit more about it. But I will not take that up right now because I want to emphasize why this argument is not very correct. Here we are assuming that log of f of x is differentiable, which we cannot do unless we know that f is differentiable. So to the person who suggested this as a method, do you see what the flaw in this argument is?
Yes, sir.
There was another person who initially suggested this approach.
Yeah, fx should be differentiable in this case.
You have to prove that. If you want to use this method, first of all, you have to prove that f is differentiable. How would you do that? You have to, so the first principle way of doing it would be you have to show that for every x, this sort of limit exists. Only then you can say that this is differentiable, right? But
Sir,
that's
but
a
it
very
will become
difficult thing to do.
tedious.
Yeah, it will become tedious, but instead we'll take inspiration from this sort of logarithm argument itself and say that f of x is x to the x. I'll just rewrite this as e to the x log x. Can I do this?
Yes.
Now, what are the things that I can use? I know that composition of differentiable functions are differentiable. Log x is differentiable, x is differentiable. So x log x is differentiable.
Yes.
So e to the x log x is differentiable.
Yes.
So f is differentiable. I'm using properties instead of first principles and just rewriting the given function in a way that matches the properties, and then I can use this, or I can just use chain
So
rule
you are
and do
writing
it
the
further.
function in a way that the function which is defined is differentiable, made up of
Yes,
differentiable functions.
yes, it's products, compositions of all differentiable functions, so it's a differentiable function. So this, for your course at least, such a thing is not relevant because this is a theoretical argument. Most of the time you'll be dealing with uh, simpler functions and numerical problems. But this is one thing I wanted to point out, that many times we make such assumptions. We take log on two sides and then do the problem. That's not always mathematically precise. I hope that point is conveyed.
Yes, sir.
All right.
Yes.
The
I
answer
thought
is correct. So
we define a
here it happened.
yes.
Sorry.
I thought if we define a argument only that it should be correct, so it might be good, but there was another way.
Yeah. This x plus h to the x plus h minus x to the x divided by h. This is not how you're going to go about proving that it is differentiable. Most of the time, as I was telling you earlier, using the properties of uh, sums, products, compositions, you can prove that something is differentiable. All right. Now you don't even need to take the log. Okay, so here I can just continue this as e to the x log x, use the chain rule, times the differential of x log x, which is just log x plus 1. And e to the x log x I can rewrite as this, and I'll get the same answer. I should get the same answer. But that small thing is something that you have to take care of. All right, so we'll go to the next question, which is a routine question. Maybe take a couple of minutes, maybe until 9:27, I'll start discussing the solution. So here you're not just asked for continuity, you're asked for differentiability. So yeah, try this problem and then we'll discuss this.
Sir, are A and B equal?
I don't remember the solution, I think. Let me just check. I don't think so. No, they're not.
So A equals 2 and B equals to 3.
Yes, that's correct. Maybe we start discussing.
First one is a plus b x square, right, sir?
Yes.
Okay.
And the second is 3ax minus b plus 2. So this is the solution. Now, this is the answer. Now let's go through the solution. So once again over here, there is a small mathematical point that I want to showcase. First, yeah, let me hear. So what are the things that you have considered?
So if it is differentiable, then it looks like a plus bx square equals to 3ax plus minus b plus 2.
For all x?
Means less than 1 and more than 1.
So the first point is that probably this was not mentioned in the summary session yesterday. It is an important point. This has to happen.
Yes.
Okay, so now can you get a relation between A and B using continuity? What is the left hand limit? What is the right hand limit? They have to be equal, right? For continuity in the first place.
For continuity means f of 1. For f of 1, both of these would be equal.
So f of 1 is 3a minus b plus 2. This has to be equal to the left hand limit, which is a plus b.
A plus
It's a
B.
polynomial, so I'm just substituting, which is also equal to substitution of 1 in the other equation, which would be the right hand limit, but I'm not writing that again because it is redundant. Now this will give me a minus b plus 1 is equal to 0, I think. Right? Rearrange, I'll get this. Now there are infinitely many a and b which would solve this condition. But the thing is that when you look at the graph, you're interested at this point x equal to 1. There is some quadratic equation on one side. There is some linear equation on the other side. This would lead to some sharp point generically. Like it is not enough if I say that the limits of these two are equal. For different values, you might get a sharp point. So what you would want is something of this sort, where the quadratic equation, the slope of the quadratic equation at this point is actually equal to the slope of that straight line. Are you understanding the graphical
At that point,
Yes, sir.
situation?
x is equal to 1.
Sir,
Right.
but if there is a curve and a straight line, so my slope will change drastically, right?
Now, at this point, the slope of the quadratic and the slope of the line can be the same, right? And then after that, it continues to be a straight line. So the slope doesn't change really. So for example, take just x square, right? I can chop this off at some point. Let's say I'll just chop this off at this thing. So this is f of x is equal to x square, and this is, let's say, the point x is equal to 2. Over here, the slope is 4. So I have this point 2, 4, and m is equal to 4, let's say. This is what I want. Can I not have a line with these properties? I can. Y minus 4 is equal to 2 times x minus 2, which is y is equal to 2x.
Sir, but the M equals
So
to
if
2.
M has to be 4, no? So here the f prime of x would be 2x. And the slope of the quadratic at the point 2 will be actually 2, not 1. Sorry, it'll be 4, not 2. Isn't it?
Yeah.
Yeah, sir. Yeah.
So I can have this. I can have, well, this is not a very good diagram, but I can have a straight line beyond this, something like this, so that there is smoothness at that point. So that's not an issue, right? You can have, you can just calculate the slope of the quadratic at some point and then continue using a straight line with the same slope. There you can guarantee smoothness. Right, so that is what you
It's
have
like
to do over
tangent
here
at a
also.
point.
Sir, one thing is that there is two equation. One is quadratic, one is linear equation.
Yes.
So,
Yes.
it means they are means they have some intersection point. When they are equal,
Okay.
so they are intersecting at some point. But
Right.
does that mean that at that intersection point, both the quadratic equation and the straight line slope would be same?
Yeah. Otherwise, you would have a corner, right? So what happens when you have a corner? You have a slope to be something, and then slope suddenly drastically changes, despite it being continuous. What do you need to have smooth slope? So suppose if you want to have smoothness and no corner, the slope at this point for the
Then
quadratic
it will.
and
Then it will
the
not
straight line
become.
has to be the same.
No. What I am
So if
saying,
you simply, yeah,
because this here the b is a positive, so it is a upward parabola.
so I don't know this. So a priori, I don't know this. So you don't need to assume that it is positive,
नहीं a plus bx square. So b
right?
here I assume that ki b is positive. Huh?
You
So
cannot assume just like that.
acha.
So just by the given data, you have to figure it out.
No, my confusion is the parabola and a straight line. They are intersecting at some point. So does
Right.
that mean that the slope of the parabola and the slope of the straight line at the intersecting point would be same?
For differentiability, yes. Otherwise, if you have a parabola and a straight line like this, you'll have a corner. You'll not have a tangent line over there.
Then
Right.
it will become discontinuous.
It is not discontinuous. It is continuous. That is a important point. It is continuous, but it's not differentiable. Continuity deals with jumps and so on. So this thing is not. This is a perfectly continuous function. But
Okay,
here you
sir.
have these corners,
Okay,
right?
sir. Understood. Yes.
So what about mod x? Mod x is a continuous function. But the problem with mod x is that there is a corner. So corners are something that we avoid. If you don't have this line and the parabola slope to agree, you will have a point where the tangent is not defined. Right? Otherwise, what would the tangent at this point be? Would it be this or would it be this?
Okay, got it.
Okay, so that is the reason why we talk about differentiability when we talk about tangents.
Yes, we would like the notion of the direction of the graph at every point. For example, for the modulus function, at this point, what do you say is the direction of the graph? You can't, right? There is no.
Yes.
So on one side you have this, on one side you have this. So at the point of change, there is no direction. So here, once again, there is one subtle point that I am looking over. We are talking about continuity of derivative rather than differentiability, which is a slightly stronger requirement. Don't worry too much about that. But the slopes, why the slopes of this and this have to match? Do you understand?
Yes.
Yes, yes, sir.
Yeah. So the slope of this is something like 2bx, right? If I do the differentiation just using, since these are polynomials and so on, and just use the usual things. These are the slopes. Is that okay?
Yes.
And I have to have them to be equal. At 1. So it's 3a is equal to 2b. So you have 3a is equal to 2b. And if you solve these two equations, you'll get this.
Sir, I have always this confusion was that this differentiable and this continuous. Suppose we have a smooth curve, like
Right.
parabola or a
Mhm.
polynomial.
Okay.
They are the smooth curve. They have several critical point. So at
Yes.
each critical point, their slope is 0.
Yes.
But that critical point, their direction changes.
The direction changes is not a problem, no? So if you have a straight line, it goes from positive to, negative to positive as you pass 0.
Sir, I have
It
doubt
is still
that.
it is still
In the
this thing.
mod
So when
X,
you're talking about a critical point, over here, your derivative is 0, but it is gradually turning from positive to 0 to negative. That's okay. Isn't it?
okay. But
Sir, why is it?
then what will happen in the case of mod X? Because that is a sharp change or abrupt change. That's why.
Yes, yes. So over here it is -1 all the way up until here, and then it is suddenly +1. So smoothness means there has to be gradual change. So if you plot the graph of f prime of x, what happens over here? It is -1 and it is +1. That's a discontinuous thing. This is f prime x, okay? This is not f of x. So that sort of thing should not happen. Once again, I'm going to tell you that there can be differentiable functions with non-continuous derivative. But abrupt changes of direction of the thing, direction of the graph should not happen. Suddenly you can't go from -1 to +1.
Sir, that why it is considered that if a function is differentiable, then it is always a continuous?
This is a result. You can prove it using the sequential definition itself.
Sir, by first principle, we can prove it.
Yeah, so if you have like x plus h minus f of x divided by h, you should start out with this
Multiplying it
condition
both
that this
sides with
exists. Yeah, then you'll take this minus f prime x times h is 0. Okay, there's a proof of it. I'm not going to give you the proof. I probably don't even remember it right now. But this is a result that you can assume. I think the prof proves it in the lectures, or at least
Yes,
gives
sir,
a
it
sketch
is
of the proof.
proved in the
sir.
lecture.
Okay, sir.
Yeah, you can take a look at that if you want. The other implication, of course, is not true. F is continuous does not imply it is differentiable. Mod x is an example. Okay, so let's take a look at the last question that I have, and then we'll also look at x mod x, which I had promised yesterday. I had also promised x sine 1 by x. So I'll take up that also, but we have x square sine 1 by x over here. Solving this should give you an idea of how to do that. Now discuss continuity.
I
Sorry?
also see question in like that x into sine 1 upon x.
Okay, let's do that too. Discuss continuity. Let's first do this and differentiability.
So basically it is continuous.
Why is it continuous?
Because I think that LHL and RHL both are equal states.
RHL is okay. Why LHL? There's only one statement that you have to give. I'll be convinced that you know why it is. LHL is also 0. Since we are a little bit short on time, I'll
Sir, can we use
start
x
discussing.
as 1 by x sign in denominator? We can write it as 1 by
We
x.
can do this by the squeeze theorem as
Yeah, sandwich theorem you can use. So that's what we will do.
x will
So
tend
for
to 0.
I'll get to it. Let me first. So first of all, other than points, other than x is equal to 0, everything is fine. Continuity, differentiability, everything is fine. So I'll just look at 0. RHL. For RHL, what is the behavior of the function to the right of it?
It is
X square.
parabolic nature. X square, yes.
I can just substitute and get
Yes.
the value 0. This is also equal to f of 0,
F of
which is 0. What about LHL? This is what I want. I want to know whether the limit as x goes to 0 minus of f of x,
Sir, we
which
can write x
in
square
that,
as x into sine 1 by x upon 1 by x.
how would that help?
Sine 1 by x upon 1 by x will turn 1 and x which is multiple will turn out to be 0. So 0
I'll
into
also
1
take a
is
look at that argument. So, okay, what you're suggesting is doing the following, right? X square times 1 by x, I can write this as sine 1 by x divided by 1 by x.
yes, sir. Yes, sir, this way.
But why would this
Or
go to
else
1?
just an intuition.
Sine x
Like,
by x
hello.
is equal to 1. That way
Okay. Wait, I'll deal with the other question also. So first, let me.
I have a thought, like since LHL you have x square into sine 1 by x. So if you put x in here, so some 1 by that will turn to infinity. And again, this will x, you are multiplying 0 by anything. So it will again tend to 0 only. It will become 0 only.
Yeah, but what about this? Why is the limit of this equal to 1?
Sir, we have done sine x by x as limit x tends to 0 as 1. So I am just comparing I am just making that.
Okay, but is the argument going to 0 over here?
No, that is
Sine x by x. Sine x by x goes to 1 as x goes to 0, but does sine 1 by x by 1 by x go to 1? It doesn't.
Sir, the graph is oscillating around 0. Is it that?
Sir, but 1 by x is infinity. So we can use L'Hopital's rule as sine. We are getting infinity by infinity.
No, sine infinity, that doesn't go to anything, right? It doesn't go to infinity. It does not go to infinity. Because sine is always a function between -1 and 1. How will it go to infinity? So
Okay,
this
it is
one will
applicable
not
only
work.
okay.
This method doesn't work. At least the arguments that we have seen so far doesn't work. Maybe there is a way to make such a manipulation also work, but the things that this identity or L'Hopital doesn't work over here. Okay, this method
Okay.
doesn't work.
Okay.
So you need to be careful as to where the limits are going. So only when the limit when the argument is going to 0, you can say sin x by x is 1. So here the argument is not going to 0. So then you cannot use this result. L'Hopital you cannot use because this is not of the form infinity by infinity. The denominator
Okay,
is going
so
to
if
infinity,
x
but the
tends to
numerator is not.
infinity, then I can use this.
Yes, if x tends to infinity, you can use it. Yeah.
Yeah,
So
then
now what we will do is use, as suggested by one person earlier, the fact that this can be sandwiched between these two functions. Is it clear why that this is true?
Yes.
Right. What about the bounding functions? Where do they tend to as x approaches 0?
Bounding, I mean,
So
This function and this function, what is the limit of the two functions as x goes to 0?
will be, I think, that 0.
Yeah, both of them are going to 0. So if the function which is the lower bound as well as the function which is the upper bound, both of them tend to the same limit, then the sandwich
and the
theorem says
middle one
that
also goes there.
Then function also go to 0.
Then also center will be goes to 0.
yes. So now, okay, here we are only talking about minus, but even plus you can do it the same way. This will also go to 0. Is this fine?
Yes, yes.
Yes, sir.
So whenever there is a sign, think about using sandwich theorem because it has a nice bound. Not always will it work, as we had seen yesterday in an example. But in this case, it does. So 0, function value is 0, left-hand limit is 0. So we have continuity. What about differentiability? Can you guys take a couple of minutes and see if it is differentiable? Or maybe just tell me what you're thinking, or like how are you approaching this problem of differentiability?
So can we apply UV rule? UV and a chain function.
So this is why I actually wanted to bring up this problem. So what you're suggesting is the following, right? So you look at this function x square sine 1 by x, and then you differentiate it using the product rule. So it would
And
be
you
x
have to
squared
use the chain function.
cos 1 by x times this. So upon differentiation gives me 2x
Sin 1 by
sine
x.
1 by x,
Sin 1 by x.
which when I simplify becomes minus cos 1 by x plus 2x sine 1 by x. Right?
Yes.
yeah,
On the other side, I have x squared. So this guy becomes 2x. Right? Now, what about this guy? Does this guy have a limit?
Can't say actually.
Yeah, it's have
What
the
about x sine 1 by x?
So
Sir,
0.
likewise it goes to 0. by using
X sin 1 by x
program.
goes, right? Because x
Yes.
x sin 1 by x can be bound between minus x and
Sir,
plus
but
x.
we can say that cos 1 by x oscillate many times during the time
Yes.
interval. So we
Yeah.
cannot.
So when
Yes.
yeah, so this thing doesn't have a limit. So the whole thing doesn't have a limit. So this does not have a limit. As x goes to 0. But this, of course, does, and the limit is 0. So can we conclude that this is not differentiable?
Yeah, sir, because
We should.
Sir, please
So-
come again of this thing that d of x, this expression, why this is no limit.
yeah,
So
sir,
when you have
because
this term cos of 1 by x, so when you go closer and closer to 0, either from the positive side or the negative side, it doesn't matter. What happens to 1 by x? 1 by x goes to infinity, right?
Yeah.
So means it takes, it doesn't matter how far you, the values do not converge to, there are infinitely many points where it is, the cost value is, say odd multiples of pi by 2. It becomes 0. There are infinitely many places where it is 1. There are infinitely many places where it is minus 1.
yeah, then
So when you look at
ultimately
the,
minus
so you'll
minus
have,
cos x 1 by x.
Okay.
you'll have something like this. All of these points, there are infinitely many of them. There will be plus 1. There are infinitely many of them where it is minus 1. There are infinitely many of them where it is 0. So it does not approach one particular value. It's oscillating all the time. So if you want to have a limit at infinity, eventually they have to all come towards some real number, correct?
Yeah, and same thing happens with sine 1 by x also.
For sine 1 by x, it happens, but since it is also multiplied by x, which itself is going to 0, by sandwich principle, you'll have that this part
we are
of it
bounding the sine 1
converges.
by x function
Then
by
then
multiplying
ultimately
by.
it goes to 0. Then ultimately both of
This part does, this part keeps oscillating. So the whole, the
Yes.
sum keeps oscillating. So it cannot have a limit. So this can be made arbitrarily small. This can be made as small as you want. It goes to 0. But this guy keeps going between 1 and minus 1, the first part. So the sum of the two things will keep oscillating, right?
So sir, can we say that we for 1x we have so many y's?
What do you mean by that?
Means we are not having a function. We are.
This is a function. That is a function, all right. But it is just that it is oscillating very rapidly near 0. So that's why it is not, this does not have a limit.
yeah, that's one rotor apple spoils the whole bear.
Okay, that's maybe one way to look at it. Yeah. So the thing
Because
is,
it has no limit, so it is not differentiable.
no, that we have not said. I said that can we conclude that? So the point that I want to say is that this cannot be used to conclude that f is not differentiable.
Yeah, sir,
So
understood.
first, so this cannot be used. Okay. In fact,
Sir, if we use instead
f
of
is
x,
differentiable.
excuse me, sir.
Just one moment. Let me just make this point, and I'll tell you why this is not possible. I'll take your doubt a little bit later.
Okay, okay, okay.
So what we are doing, actually, what we have done in this process is not used any first principles or anything. We have used this this function, this expression for the function. We have differentiated it and then taken its limit as x goes to 0. What we have said is that limit as x goes to 0 minus f prime x is not equal to, or I mean, it does not exist actually. So this does not say anything about the differentiability. I'll tell you why it is differentiable now.
Sir,
Now, if you want to say that it is differentiable, you have to, just going by first principles, you look at the following expression, right? Now, let me just do minus, since that is what we are interested in. Limit as h goes to 0 minus f of 0 plus or f of h minus f of 0, since this is, I'm interested at the point x is equal to 0. What is f of h? It would be h square sine 1 by h.
sir, but by the function we are not able to determine the rate change. And if we are not able to determine the rate change, how can we say it is differentiable?
I'm saying that you can determine the rate change, and I'm saying that this is not a correct method because we have differentiated the expression which is to the left of 0 and tried to approximate the slope using that. That may not be possible.
Absolutely, yes.
Okay.
Okay, so we have not looked at the first principle definition. Now, what does the first principle definition say? If this limit exists, then you're good to go. That's the rate of change. So if I put x is equal to 0 in this expression, I'll get f of h minus f of 0 divided by h, which is h square sine 1 by h minus 0, because at 0, I have the expression to be x square, which is equal to 0. So what I end up with is limit as h goes to 0 minus h sine 1 by h. And what is this? By sandwich principle, or by what we have
0.
discussed? This is 0,
So,
right?
Zero.
Similarly,
Right.
limit as h goes to 0 plus, you can do f of x plus h. You don't need to because it's x square and it's a nice, well-behaved function. But let's do the first principle approach itself. H goes to 0 plus. Once again, we want at 0. So f of h is just h square divided by h. This will just become h, and this is also 0.
0.
So limit as h goes to 0 of f of x plus h minus f of x divided by h exists. I mean, this is not, let me just do this. Exists. Therefore, f is differentiable at x equal to 0, and f prime of 0 is 0. This is the rate of change. It's a critical point. But what we have to clearly look at is what were we doing wrong over here? It seemed like something natural, but what we expected was that f prime as a f prime as a function should be continuous. That is not necessary. You can have a differentiable function for which f prime is discontinuous. That is okay. Okay, so this is once again a very theoretical. To understand differentiability is really good, and I think there was a point yesterday that was raised where I was trying to derive the formula for the derivative by first principles, and you just said you can just
Yeah, so we don't.
use the table.
yes.
So I'm saying that just using the tables and the laws and then taking it to a certain number does not always work. The principled method to do it is using first principles. And when you're using properties, you have to make sure that the continuity requirement is satisfied before you use it. Over here, that is not satisfied. The function itself is continuous, the derivative is not. So it has certain behavior to the left, it has certain behavior to the right. But simply because it's defined like this, you cannot differentiate this expression, take its value, take its limit as you go to 0 and call it, expect it to be the derivative. That is not, you don't have a justification to do that. So whenever there is a piecewise function, so if there is anything, despite all the confusion that this might have caused, I'll write something that definitely you have to use in your problems. Whenever a function is defined piecewise, meaning it has a different behavior to the right and it has a different behavior to the left. Use first principles. This is something that you will see also in math 2 later on, where there are something called partial derivatives and so on. So you can't just take the partial derivative and take its limit and expect it to be the partial derivative at a certain point. Continuity of partial derivatives and all that you will see later. Here, even if you have not understood this, the solution to this problem entirely, this whatever is written in the bracket over here, which I'll just emphasize by doing this. Wait. This thing you can keep in mind. You cannot differentiate a function and then take the limit and expect it to be the derivative at the limit point. The derivative of a function, even a differentiable function, need not be continuous. So whenever there is a piecewise function, use first principles. This is a good takeaway. And I would also suggest you to go through this solution and see that that is what we are doing. Whatever we have explicitly forbidden in this box, we have done it and we have run into a problem. The first principle approach does say that the function is differentiable. And if I don't do that, and if I follow the wrong intuition, I will land in trouble. Okay, is that all right?
Sir, here we use the sandwich principle. So the
Right.
means minus x square plus x square, and between this trigonometric expression comes. So how this minus
Yes.
x square also 0 means above is there?
So
is
you're
only-
taking a limit as x goes to 0, right? You just substitute.
Oh,
I have some operational query.
1 minute. Let me also do this x mod x, which I had said that I would do. I hope the person
Hello.
who asked the question x mod x
Yes.
is here.
Yes, sir. I'm here.
Yeah. So what was the issue with this? To prove the differentiability of this, is it? Or to check the
with the first
differentiability?
principle.
Okay. So for the first principle, what is it that you have to check? You have to check whether the following limit exists. Again, for this function, the only point of interest is x equal to 0. That is fine, right?
Yes.
So this is the expression that you have to check whether this limit exists or not, to check differentiability from first principles. Okay, what is f of h? It is h mod h minus 0 divided by h. So all you need to know is whether this limit exists. Does this limit exist?
Is it equal to 0?
Yes.
Yeah,
It is equal to 0. You take the left hand limit. If there is a confusion because it's a modulus function, take the two separate limits. Take left hand limit.
that minus h and h.
Modulus of h is limit as h goes to 0 minus of minus h, because you're to the left of 0. Doesn't matter, because when you substitute, you'll still get 0. The right hand limit as h approaches 0 plus mod h is
That is
as-
positive h.
That is h. Once again, it will be 0. Both left hand limit and right hand limit are equal, so this limit exists and is 0. Now contrast this with what happens when f of x is equal to mod x itself.
Yes, that's only the doubt. Mod x is not differentiable.
Yeah, so in this case, what is the limit that you have to consider? It is 0 plus h minus f of 0 divided by h once again. The limit of f of h is mod h minus 0 divided by h. In
mod
this
h by-
case, you're not dealing with simply mod h, you are dealing with mod h by h. Okay, now let us look at the left hand limit and right hand limit. When I am to the left of 0, what is the nature of mod h?
Minus h by h.
Right? This is what I'm interested in. And I get the constant function -1. What is the limit of the constant function?
Constant.
The constant itself. Now, when I compute the right hand limit, h goes to 0 plus I have mod h
Positive one.
by h. Now you'll see that mod h is h, so I just have h by h and I get plus. So the two limits are not equal, right? And that happens because you have a mod h by h. By multiplying x mod x, you're only losing one x by division with h. So on top, you'll just have a numerator, which is just mod h. So whether it is plus or minus, since the quantity itself goes to 0, it goes to 0. But here, this becomes something like a signum function.
If we
And compare this with a graph of the thing. So over here, you'll see that the slope is always -1. That is the nature on the left-hand side. That is what is mathematically given over here. And over here, it's always +1. So their limits cannot be the same. Right?
So
now, if I look at x mod x, let me just draw the graph over here. So here you have -x square and x square, right? X less than 0 and x greater than or equal to 0. So what is the graph? The graph looks like -x square over here and plus x square over here. This is still fine. Now, this is not an argument. This is just a visualization. The argument is over here. But if you're confused as to why x mod x would not have a corner, you'll see that it is actually -x square and x square, which will actually smoothly intersect. When compared to this, where you have y is equal to -x and plus x, which intersect in a corner. Fine. Is this okay?
That means, sir, this function is differentiable,
If
but
we can scroll below.
mod x at x is not at x is equal to 0 is not differentiable.
It's not differentiable. This is what we have been saying all the time, right? Because it has a corner. And now we have proved it also.
It's minus in RHL because mod of h, when it's less than 0, it's
in
negative.
LHL, you have a minus because mod h
yes.
is equal to -h when you are less than 0.
Got it.
So, sir, in this way, if we take mod of x to the whole square, that is also differentiable.
Mod of x to the whole square is just x square. So it's just a quadratic function.
Yeah.
Right? Because mod of x square is either -x square or plus x square, depending on whether you are on the positive side or the negative side, but both of them are x square. I think about that. Mod x square is just x square. So yeah, it is differentiable. The answer to your question. So whenever there is confusion, you just go back to this limit,
First principle,
simplify it, and see whether when you're coming from the left or where you're coming from the right, do you get the same answer. In the case of x mod x, you do, because the denominator h only cancels out with one term and there is still one term, one h remaining above, which whether it is plus or minus, it will go to 0. But there is only one modulus of h term when it comes to the function f of x is equal to mod x. That does not get, well, that gets cancelled, and depending on which side of the 0 you are, it will give you -1 or +1. So that limit will not match.
So that if we cover one more layer of mod in that mod X, then
What do you mean mod of mod X?
yeah, sir.
But mod X is always positive. So mod of mod X is again just mod X.
Okay.
Sir, are we
Right, because-
defining that the property of the function also means how the rate is changed?
I could not understand you. Could you repeat that question?
That the property of the function determines the rate change of that function.
Well, the rate of change of a function is a property of the function. So,
Like if we multiply x, that bounds the mod x. And so the rate change is, we can determine the rate change, but in here it acts like a signum function. So we are not
the
able to.
derivative acts like a signum function.
Yes, yes.
Yeah. So in general, if you have a polynomial function, you will have the derivative to be 1 degree less polynomial, right?
Yes.
So if you have the original thing itself to be of degree 1, it's not a polynomial, it's modulus of a polynomial. Your derivative will also be a degree of the 0 polynomial, which is a constant. But
Yes.
since there is a modulus, it will be a different constants in different places. That's a problem. All right. So this is where
Yes.
we will stop unless there are other doubts.
Excuse
I
me,
have
sir.
some operational question.
Okay.
Actually, I have done the week 2 mock, and like as we are aware, like while doing mock or any assignment, we are being giving like we can submit the assignment n number multiple times before the due date. So yesterday I
Okay.
did a part of the question, but when I submitted it as a final assignment and provide with the grades. So
Oh,
now
you are
if I'm
not
trying
allowed to take it multiple times, is it?
for me, I think it is yes. I don't know about the others. So now what it is, if I'm trying for the second attempt, it would give me a fresh set of questions. So again, it would consume another some time for me to solve those.
Okay, I'll bring this up.
I've
Just
highlighted
one
this
moment.
to the session TA, Manish.
Okay. Then he'll probably take care of it. There's
Just
a
wanted to
session on
highlight this
Tuesday,
because
which
this
I'll
is also
be.
in stats also. Same with
Okay.
stats.
Okay.
Sir, that
There has been a
excuse me,
new
sir.
portal thing. Maybe it's because of that. I don't know. Let's see.
Excuse me, sir.
Multiple submissions allowed is given. Your most recent submission is considered. Okay, so the thing is, you want it to be like the practice assignment where the previous answers given should be recorded so that you don't have to do them again.
Yeah, because it would
Yeah,
take
yeah,
another
correct. That's
time for me.
right. Yeah, I'll bring that up. If it doesn't get resolved by Tuesday, you let me know. I'll be taking the session on Tuesday.
Okay. I have solved 70% of the question, only 5 or 7 were unattempted out of 14.
Okay. Now it's like a fresh thing. You have to do everything again.
Again from scratch.
Okay. I'll bring this up.
That
Okay.
these things
Very
Sir.
helpful.
sometimes happens when we do the the submission na. Sometimes in the left hand corner it shows that ki not saved. When it shows that ki not
Okay.
saved, then if you close it and submit it, then the next time it might happen ki that question will not submit it. So that question again resurface.
Okay. Fine. I am not very aware of this, but yeah, I'll tell the TA to take care of it. And yeah, hopefully it'll be resolved soon.
Sir, how will quiz 2 be, sir? Can you give us any insight about that?
Well, it will. That is a very vague question. Uh, Difficulty level
Sir,
will be
I think that
similar, I think, as quiz 1. There will be a
Yes,
mix
sir.
of easy, medium, and hard questions as usual. I can only give you generic
But
responses
sir,
more than that.
and
Yeah. And
Okay,
you know
sir.
but
the
sir,
syllabus and all
and
that, right? It's just week 4 to week 5 to week 8.
Yes, sir.
sir,
And
Anthem is
beyond
Anthem.
that, well, yeah.
Yes, sir. Thank you, sir.
Uh, Try to get the mock done. I think that usually it is designed in such a way that it gives you a good idea of what you can expect in the exam.
Okay, sir.
Sir,
And
I took that 4 courses. Hello, sir.
yeah, go ahead.
Yes, sir. I am a standalone person and I took 4 courses. Which it will be
Okay.
is hectic for me or not?
For a standalone person, I think four courses is expected. There are some number of hours that you need to put in and all that, right? So I hope you have taken a look at that. And as long as you're meeting those, it should be fine.
Because sir, I also prepared for UPSC Civil Services examination. That's why.
Aha, well, I cannot be very aware of your situation otherwise, but for when it is a standalone, it is expected that you're not doing anything else. And 4 courses can be a bit much, and there might be some sections which you find difficult, like maybe graph theory you'll find difficult. So I cannot really answer that question without knowing more details about how you approach things. So for a person who is not doing anything else, taking 4 courses is doable, is the general guideline. But then again, speed of learning and all that varies from person to person. But since you have, even if you do not get everything done in one shot, you have multiple attempts that you can go through. With all those things, I think it is definitely doable.
Yes, sir. Sure. Thank you.
All right. Okay. Any other question?
Hello, sir.
So for me, should I be going for reattempt or luck? How is it? For
What is your
the
situation?
mock
I'm
2.
not sure.
Mock 2.
Mock 2 right now, I think if you have to answer it again, and
I guess it
I
would
don't think there is
provide
a
me
way
a
to.
fresh set of questions.
Oh, it's the questions itself. They are different, is it?
No, in the notification I got, like, are you going to start a new session, reattempt? Then I guess it would provide me a fresh set of questions where I have to attempt it from question 1.
I am not aware of how these things work. I'll ask the course lead and I'll let you know in the next session.
Sir, that in which
Are they graded? Like, are the mock graded? Or it's just for
I
the
think
practice?
there is some refer to the grading document. No, in that you should be given all the data. Let me look at the grading document.
sir,
In
what is
some
that?
courses, there are some bonus
Excuse
points, but I'm not sure if it is there in Maths 1.
Also, I feel like the syllabus for
Excuse me,
Maths
sir.
1
That
or any
what is the time
subjects.
period of that paradox?
What I was
Paradox is
saying
in
is,
May. That is already done.
hello.
Yeah, go
What I
ahead.
was saying is for the week
Mm.
quiz 2, usually the syllabus used to be from week 5 to week 8. But now for
Yes,
most of the subject, it has taken from week 1 to 8. Why is it so? Like, is the
so that's not
pattern
the
or
case with Math 1, right?
because
No, in
Yes,
that only
Math 1 is 5 to 8. It is
Math
in
1 is
that
5 to
mix
8.
of PT and
in that
English, I think.
in that English and computational thinking, it is 1 to 8, and
2
in
8 it
mathematics
is.
and statistics 5 to 8.
Okay, yeah. Different courses have their own policies. They, uh, we don't know why they do it, but
But
we believe that one
in
evaluation of 1 to 4 and 8 weeks together for a quiz may be too much. So that's why only for end term we have the entire thing with more weightage for the later weeks.
okay, so if I got it correct, for Maths 1, it's week 5 to 8, and for the rest,
Yes,
it's 1 to 8.
No,
I
in that
don't know about
statics
the other
also.
courses. The other courses, they'll give you the data in the form of a sheet or in a discourse post or something. I can only tell you that for Math 1, it is 5 to 8. The others you have to
Any
check with.
fellow
I
candidate can respond to this.
I got that message that in mathematics and statics it is 5 to 8, and in English and computational thinking 1 to 8.
Okay, thank you.
It's okay.
All right. Any subject questions
Hello,
before we
sir.
wrap up?
Hello, sir.
Yes.
Sir, I wanted to know something about limits. Can I ask?
Yeah. Yeah,
Sir,
sure.
sir, when we evaluate LHN and RHL, it's pretty much very simple that we just substitute that point which we want to evaluate, and we got the answer about LHN and RHL. So
Yes.
how can we evaluate using the exact definition which is provided in the lecture? Can you tell us about it?
So the evaluation of limits doesn't have an algorithm, as I was saying yesterday. The definition says that you have to prove that given any sequence that converges to the point of interest, the corresponding function sequence has to converge to one particular limit. So if you want to say the limit does not exist, one way to do it would be to provide a sequence that does not converge, or to provide two sequences which converge to different points. Now, proving that the limit exists is a harder thing. And sandwich theorem is one tool which can use to be conclusively which can be used to conclusively conclude that the limit exists, but otherwise you have to substitute or modify the expression. So when would substitution not work? When there would be some ratio. A common pattern is when there is a ratio and there is something in the denominator. One way to deal with denominators which vanish are to also check if the numerator also vanishes, and then use L'Hopital's rule if the functions are differentiable, which usually they are. You won't be given a non-differentiable function and a differentiable function, a ratio of that or something like that. So the tools that you have are sandwich theorem, substitution, uh, algebraically changing the expression so that you get the problematic term cancelled, or L'Hopital's rule. So these are the things that you can use. So the examples that I considered today, they were very simple. I was just focusing on the part where you use the right definitions for the right and left part, but the actual computation of the limit itself was not that difficult, except for these last few questions where you had these x square sine 1 by x. Here you can see that how do I compute the limit? By using sandwich principle. Whenever there is a bounded function, this can be done. But if not, then you'll have to uh, do some modification of the expression to get it into a manageable form. And there is no one method that works for all.
Actually, I was asking because the definition says that what you told about the sequence thing. That's why I was asking.
Right. So just using the definition, proving that the limit exists is not a practical way of solving problems.
So we can use the L'Hopital rule and this sandwich theorem or substitution.
Yes. If either of those three work, then you're in good shape. And then there are certain limits that you're expected to know, things like 1 plus so for sequences, at least, it is 1 plus x by n to the power n that goes to e to the x, and those things they are listed in the lecture videos. Some certain sequences you just memorize. Even log of 1 plus x by x, even though you can do it by L'Hopital, there are certain limits that it is better to commit to memory.
Yes, they have
All
given
those
that.
things, whatever there is in the props videos, you can take that as things that you need to know or memorize.
Yes, sir.
All right.
Okay, sir. Thank you.
But especially due to the nature of the exam and the nature of the course, giving the theoretical proof that every sequence that converges to the point, the function sequence converges to a given real number, is not the best way to go about it, even though it is the most precise one and the most mathematically correct one. Well, L'Hopital's rule and all those things are theorems which are mathematically correct, so there's nothing wrong with them. Maybe I should take back my previous statement. But in general, there is no checklist that do this, do this, do this. If this happens, then the limit exists, and if this does not happen, it does not exist. There's nothing like that.
Okay, sir.
The only way to get better at it is solving more and more problems, and hopefully the set of problems that we have given you will train you well enough.
Sir, when will we do the PYQ?
Probably the TAs will take that up in the revision sessions. The revision sessions should be scheduled in the next week. So,
Sir, can you tell the approach to a question? Like for this set of questions.
so during this
any
session,
log
the
or any
entirety of
equal-
this session, I have tried to motivate that itself, how to approach a question rather than just give you the solution. And
Yes.
there is no general way to work through every problem, right? Like every problem is different. The more
And
you
sir-
solve, the more intuition you get as to what would be the right approach.
And sir, in a logarithms, I face much of the problem, complex log problems.
Okay.
Like-
Maybe during the revision sessions, you bring a set of questions that you are struggling with, and we can see where the problem is.
Sir, in that
Okay.
Maths 2, which content released that some?
Why are we talking about Maths 2?
No, I'm just asking that which syllabus and.
Maths 2 has multivariable calculus and linear algebra. Multivariable calculus is some sort of generalization of what we are doing right now, continuity and differentiability for functions with multiple variables. So in this case, you have functions from R to R, right? Like there is one input, there is one output. In Maths 2, you will have multiple inputs like R3 or R2 to R functions,
Yes.
and measuring rate of change of those functions. Linear algebra is something which starts out with system of linear equations. But anyway, you will get there when you get there. Linear algebra, multivariable calculus is the broad set of subjects in Maths 2.
Yes, thanks.
And if you understand differentiability and continuity of one variable calculus, it makes the corresponding topics of Maths 2 much clearer, much easier.
Yes.
All right. I think now we'll stop. It's half an hour past the
Yes.
Yes,
scheduled time. All right. And
Okay,
bye.
thank you.
I'll see you on Tuesday.
Yes,
Okay,
Thank you, sir.
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 Thank you, sir.